And then because I realize my limitations here, I'm going to quickly go to YouTube and make sure we're streaming. It says live now. That might be something. It's awfully quiet in here. Did I ruin everything, your conversations? Go ahead and, I'm just, you know.
You can see anticipation.
Anticipation, yeah, it's for me, it's more, gosh, what am I doing? I always find it, I don't know YouTube well enough to go and figure out where to grab. There it is. They sort of, my route to find where we are is really circular. And you'd think I'd learned by now, the breadcrumbs and whatnot. But, hey, look at that. That looks like it's live. All right, I'm good with that. And the chat window is back open. Hello, everyone. There we go. Just in case anyone wants to chat. Hey, there's someone on chat. Hello, Sohi. All right. There we go. Live works well. Awesome. I'm glad to hear it works well. This is even better. Okay, good morning. It's cold here. How do you live? No, I'm kidding. I've maintained I wasn't going to complain about whenever I was going to complain. Like this is reaching the breaking point. Got to pull it back in. Take a deep breath. We can do this. If you can all do it, I can do it too, right? So first thing, I have, for those of you who submitted homework 1, I sent emails with it attached to the graded version. If you did not receive one and you submitted one, please email me. That usually means I somehow didn't file it. So work around my limitations, but I will make sure that your grade is recorded. And if you know everybody who's talked to me who's gotten an extension, that's totally cool. Just send it to me when you're ready with it. I will say that today's class is setting up homework that we're going to have, homework 2. So we've got another one coming. This one's going to be fun. More fun. Way more fun than R. Way more fun than playing with R. It's actually like Bayesian and stuff. Let's see. The next thing was sort of just a little more housekeeping. I mentioned I do this a while. How do you take notes if you're cloning the repository that we have? And how do you take notes in it and then update it to what we do, what we have when I push something to the master branch, when I create a new set of class notes, how do you update your local repository with that? And so I put together some notes on it. I will tell you, I am not a great expert at Git, so there may be better ways of doing this. And if you have a better way, please let me know, because I'm more than happy to learn from you. But what I came up with was something called fast-forwarding your repository. So this is where I put this document together, and you should be able to find it on GitHub. Here, I have a new folder called How-Tos. So How-Tos, there is a markdown file that talks about how to do this. This is starting from cloning into the repository and moving on. If you already have a cloned repository and you've made notes on some of the files, the key is this. Wherever you make notes and files, put it in a folder that's not the current name it is. So right now I have folders that are named lectures, homework, back up here. So I have homework, lectures, syllabus, and how-tos here. When you go into your local repository, rename, if you already done this, rename one of those folders, right? Just put your name at the end of it, make it something where it doesn't have it. That's the steps that are in this markdown file. That effectively gets you to the last step. This sort of says clone into the repository. You can create a new branch. This is also something that's helpful. If you have your own branch, that would be good. So one thing to do is git checkout-b, and then you put a name of your branch there, and then put the notes there. So I'm going to just do this really quick just to show you how it works. That's cool. And then you can try to follow along. If you already have your repository cloned, don't do that part. All right. when we get to branch, you can do that part. Right? So now the commands that we're going to use are going to be terminal-based commands, or if you have, so your Git client should have some type of terminal commands. And this is where my limitations are because I use the Mac operating system. It may work a little bit differently on Windows, and so if it does, let me know, and then we can try to figure out how to make that go. But there's nothing like, I tell you, there's nothing like going back to like the 80s with the command prompt, isn't it? I don't know, this was computing to me growing up. So, you know, and it's computing to me now, ironically, and there's that stretch in the middle that, oh, Windows. But, so here, what we're going to do is first clone into the repository. If you've already done this and made your repository with notes, don't do this part, okay? So, I'm just going to create a brand new repository. I'm going to change my directory to, I'll put it somewhere where I'm going to delete it afterwards. So I'll put it in the downloads folder. I grab the repository. There. Okay, that's the part you have done already. Now this is the part to do. Make sure if you've got a terminal open, you put the terminal's working directory within the highest level folder of that repository. Right. So now I'm going to be in right here. And I can tell you that because I can see all the folders in it right there. Right? And so now with that, is this something you can all see pretty well? Do I need it bigger? No, you're good? Okay. Okay, so we're in the repository. We've cloned to it. The next thing to do is to, if you already have your repository, rename the folder that you have, where you've made your notes. If you have lectures, rename it to lectures and some other word. I'm going to just create a notes folder itself, but that's effectively the job that you're doing by renaming it. So have you renamed things before on the command line? If you're familiar with it, anyone want to go over how to do that? I can. It's usually the move command. Like if you move your lectures folder, I think move is the same in Linux. What's move in Windows? Is it MV? Anyway, it's basically you move the directory to the new name, right? So I could say effectively something like this: MV lectures to my notes, or lectures and notes, right? I do that. If I type MV that, it effectively renames it. Now you have the folder is now lectures and notes, and you see a folder named lectures is just not there, right? Any questions? I feel like I'm going through this too quick. Happy to help. I want you to keep your notes. Questions? All right. So I have that new lecture file. Oh, I forgot to do this one thing. We need to go and create a new branch. So a branch in the repository, remember how branch, I don't know if I told you much about branches. In Git, the way it works is there's this main, when you see in the repository, it's called the main branch. And then typically that's the stuff that goes live. So whenever I have a brand new lecture, like yesterday, I push to the master branch the lecture materials, the new homework and everything. I had been working on that all week, actually for quite some time. And the lecture materials in the branch, I was working in my own branch locally, so I wouldn't overwrite something in the master by accident. And so how you change the branch is to go and type the word git checkout -b, and then we put a name of your branch there. And so this is where I would just put something like my notes or something like that. And so then what happens is you do that, and all of a sudden it said, all right, look at that. I've got my new branch. Switch to new branch, my notes. Let me look at the folder here. So now you see the folder structure still has my lectures and notes. That's the changes I've made in it right there. Following okay? Questions? Okay. Then the fun part happens. This is the part where you have to be really careful, right? To make sure that you don't accidentally do something. but this should be able to. Oh, actually, this is a the rebase command is a non-merge, so you won't have a record of what just happened to move up. So once you make sure that your notes are in a folder that's not one of the ones that exist on the master, right? Technically speaking, you could also rename all the files if you'd rather as well. It doesn't make a difference. Just rename them so they don't get overwritten. There's two commands that you have to write. The first is git fetch, and the second is git rebase origin/master. So if I do that, git fetch, it runs. It doesn't do a whole lot, but it runs. And then I do git rebase. Uh-oh. I have unstaged changes. Okay, so this may happen. It says git rebase. You have unstaged changes. You may see that. I need to go and modify my file to save this. My changes need a commit. I need to go and commit them to my branch because I changed the name of my folder. Now I need to commit it. So the way that I do that, if you're in RStudio, you have the little drop down, but in Git, the way to redo. Here, let me see if I can make this where you can see it. Make it a little bit bigger. There we go. It's the way that you commit your changes using the command line is to use the word git and commit, and then you put a commit message with a -m, and you put in quotes your message. I renamed lectures folder. Oh, I did not add. Pardon me. First thing you do, gosh, this is a nightmare. I'm sorry. Git add dot. Git add dot moves the files to the staging area. That's first. Git add dot. Okay? So Git's telling me I'm screwing up. So if you do git add dot, now you've got a bunch of files that are ready to be committed that you've changed. Now you can go back and do the git commit m. And now it says, here are the changes that you've made. I renamed all the lecture files, right? So that's what it shows. And now I can rebase, right? I'll just run the git fetch command first and git rebase master. And now it says it's up to date. And what happens is if we type ls to see all our files, uh-oh, that didn't work either. What have I done wrong? I practiced this yesterday. I really did. What it's done is it's taken the lectures file and combined it. So, okay, back to the drawing board. My apologies, this is where my git commands is. Hopefully you didn't do git rebase. Okay, here's where I think I did wrong, because if I do, I think it's gone and updated my lectures and notes knowing where it is. These are the branches. I don't have there's my notes. There it goes. Okay. So, okay. Well, how's this sound? Let me go back and make a better video about this. Talk to you about it. I'll just record it on my computer and push it somewhere to the website. Okay? The danger of trying to do things live. All right, what's class going to be like? Let me record that video, and then what I will do is let you know how to do it. For the meantime, go clone a new repository with another name and take notes in it, and then you can combine the files you've taken notes on with your old notes file. And I'll tell you what to do when we get there after that, okay? My apologies. Yeah, that's pretty funny. Sorry, everybody. Okay, questions or thoughts or comments, apart from like me screwing up? I thought today was going to go so smoothly. There were warning signs all over this morning. My My son didn't want to go to school, had a little meltdown before I left the house. Should have known. I should have just been like, you know what, guys, just don't even bother coming. It's going to be one of those days.
Pack it in.
What's that?
We'll pack it in.
That's right.
We're
But
good today.
You know what? But somehow, through luck, Lisa, mainly Lisa, partially maybe me, helped turn him around, and he went to school happy. And so he's at school now, and we didn't have to have a big fight about it. So just like that, maybe this started off badly, but maybe I can turn this around. All right? So we left off last time. What was that?
Leaving.
Well, thanks. Okay, going back to where we were. Do you remember where we left off the last time? What do you remember about last week? Apart from me quizzing you, and I shouldn't have done that, but I needed to know. Do you remember how we had we have this data set that has basically a linear model, and we're trying to predict someone's weight based on their height in inches and the diet group they happen to be, which again is, you can totally tell this is simulated data set because there's r squared of 0.96. It's either simulated or there's non-random assignment, right? Sort of. But even then, I don't think you get an r squared 0.96 with a height to weight ratio in non-random assignment. Anyway, I don't know, what's the highest r square you've seen with real data? You do pseudo-experimental data. Okay, so this is like r square Hall of Fame worthy. like put on your wall. I used to joke about doing that. Like if you've got an r square above like 0.5 even, bring it to me and I will put it on the wall. And like have like you know how like you put I like to put my kids' pictures up on the wall when they're drawing, right? It's like art, but it's not pretentious, right? It's like, oh, that's cute, right? Like the r square, that would be pretentious. Look at all of these r squares we've collected that are great. Yeah. Okay. So we went through all that. We looked at data. We saw that the results. We talked a little bit about the results itself. Right here, we saw there was. Let me just get back into the lecture again. This is lecture 7. I'm going to run everything up to this part, and then we're going to run this analysis right here, where we ran the linear model. We saw the linear model output. We saw each of the effects. We interpreted each of those, and we sort of said, see you later. We'll talk about it next week. Now it's time to do this in a Bayesian sense. First of all, quick question for you. What do you think Bayes brings to this that we didn't do with least squares, or what we did previous to this? What will we gain by doing Bayes? Probably nothing.
We can make different assumptions.
There.
It's cooler.
It's cooler. We have to have Bayes in this class, and it gives me an example to teach from. What I'm trying to say is there's a lot of people who are like, love Bayes because it's Bayes, and that's true. And perhaps this is a reason where we could have, if this was updated data, if we had collected a previous sample and then we collected a new sample, we wanted to update a prior, we could do that as well. But generally speaking, for this analysis, there's not going to be a lot to gain from it, but I do want to highlight a few differences you get out of it when we do this. And so we're going to do this in JAGs. Let's see here. I'm gonna knit the whole file first, and then I'll go back to it and try to compare it. Now this knitting process takes a little bit longer if you try this, and that's because a couple things. The first thing being, oh yes, of course, if you try to knit it, to try to highlight one of the differences, I had to download a package. I was really going to try to talk about the mode of a posterior distribution. Turns out that's not necessarily an easy thing to get. Right? You can talk about a mode of a theoretical distribution because you can maximize the distribution function and find it. When you've got observed data, how do you figure out where the mode is? You've got to somehow come up with a smooth density and figure out that mode point. And so there are several packages in R that will do this. The one I actually like is one called mode_est. But to load mode_est, you have to load the bioconductor manager. because it relies on packages that take a long time to load. So if you are running this whole thing and knitting this whole thing, it will be a nightmare. The other alternative is just to comment out this section that does the mode, because the installation process takes quite some time. And of course, Bioconductor Manager, when you run it, says, hey, oh, and see, it's actually doing it again here. It's installing it. Okay, I'm promising we're going to turn this around. We're going to talk about the mode later. All right, there we go. I'm going to comment it all out, run it again. Oh, I see I didn't do an if require here for the gene filter. Gene filter is a package that blew it up before too. That drives me nuts whenever you try to load a package and it loads for like an hour, or try to install it and it takes an hour. There are certain things in life you know are going to take a long time, like installing SAS. That's a nightmare. All right, here we go. So, trying to start over. What are we doing here again today? Bayes, right? Let's talk about this Bayesian analysis and how we go forward. To do the Bayesian analysis, we need two things, right? First of all, what's Bayes about? We need posterior. Get the posterior. Get the posterior, we need a likelihood function. We need a set of prior distributions. And for us, we need potentially a lot of prior distributions. So I'm going to give this a quick treatment of models. The next lecture, lecture 8, will be a little bit more thorough treatment of kind of the math behind the priors and how they work to be, I would say thorough in quotes. It's not entirely thorough. Thorough up to a point. So this is our linear model. We've got an outcome Y. I have the subscript R to represent respondent or response. And we have a set of regression weights, beta 0 through beta capital V. There are capital N people in the sample, by the way. And each of the observed predictors are X, sub-respondent 1 through capital D as well. And then there's a residual error or error term for each respondent. So that is the way I'm doing this type of work. We're going to make the assumption that error follows a normal distribution with a variance that is constant across everything. You'll note in your homework, I'm going to let you code around that. You're going to create one that doesn't have that. So let's see how that goes. So loosely, what we can say is that an observation YR is follows a conditional normal distribution. This is sort of what we were talking about last time. The mean of that, what makes it conditional, is conditional on the predicted or the observed values of X. Each Y should have a mean that's all the X values put into a vector times all the betas put into a vector, X beta, and then the residual or the variance of that distribution should be sigma squared error, the residual variance. Okay. Everything, does that work with how it's my need priors for, and sigma squared error we need priors for. So rather than, I think conceptually it's a little bit easier if we chunk all the betas together into one big vector of them. And the reason why we can do that is there's a really nice conjugate prior for that vector of betas, and it turns out to be a multivariate normal distribution. So multivariate normals sort of run linear models. They're great to use. That's where we go. So we have a vector we need a prior for, which is beta, and we have a scalar we have a native prior for that's sigma squared. Now, remember, I don't know why I do this wrong, but somewhere here, it doesn't, I get myself an error at the code. This is supposed to be a level 4 heading. Anyway, not going to let it derail me. We're going to get through this. Questions on this so far? Anything questions about the model? Okay, so what's conjugate prior? Remember that term? Conjugate prior, anybody want to just take a stab at it?
Same distribution as your posterior.
That's right, yeah. The prior family distribution is the same as the posterior. And what we're going to find out is that in linear models, the conjugate prior has a little bit of a hiccup. Because if you go and look at these two parameters, technically speaking, we could create a prior that's a joint distribution between beta and sigma squared error. But in the next class, I'll show you how we can actually go and separate these two, have sigma squared error kind of be kind of the first thing, and then conditional on sigma squared error, we can go create a prior for beta itself. So in general, we could say this prior for both of them really consists of a conditional prior for beta, meaning given a value of sigma squared, this is the prior for beta, and then a marginal distribution for sigma squared itself. So we can actually go and pick the prior for the sigma squared. When you put them both together, the posterior distribution, to make this conjugate, we need to pick values of these two things that are similar to what the data likelihood will be, so that we can smush them all together. That's a technical term, right? Smush the prior into the data likelihood and have it look like the same form as the family. And here, what we're going to find is that in the data likelihood, we can express it as what's called a normal dash inverse gamma distribution. So when we put it all together, if you look at the data distribution right here from the normal, right here, it's a multivariate normal effectively. We can rearrange terms a little bit, and we can go and say, oh yeah, this part over here, yeah, that's inverse gamma, and this part over here, that's multivariate normal. And that allows us to go and figure out this multivariate normal dash inverse gamma prior for it, for the two. So sigma squared will have a sigma squared error, has a conjugate prior that's inverse gamma. How many of you walk around being like, I totally love inverse gamma?
Reading this book, I'm getting there.
I was going to say, I don't. I know it still throws me for a loop. But if you want to see the inverse gamma, we could always go to YouTube. It's got this nice, well, the range or the support of it is from 0 to positive infinity, and so it fits with the range of sigma squared where it should be. It has two parameters, sometimes called a shape and a rate, sometimes a scale, depending on which language you're in, which package and so forth. And Lisa said, thanks God for Paw Patrol toothbrushes. Yes, we had a Snuck Huey. I sort of turned it around. Hey, look, I got this toothbrush that we just got in the mail for. Look at that. It's got a character on it. What? Get out the door. Okay, so shape and scale. These two parameters, inverse gamma is where it is. There is inverse gamma. It's so regular that R does not have it in its base package. So that's how it tells you how constantly people use it. Hardly ever, right? You can't just, like, if you're going to generate random numbers in the base package, you type R norm or R unif or whatever. There's no R inverse gamma. You have to go and download the inverse gamma package and then run it, right? So it tells you how, like, obscure this is. So it has this alpha and this beta character. And what we can tell with sort of in the history of people doing Bayes with linear models, which stretches on forever and ever, they try to break these two parameters down into terms that apply to data a little bit, which to me was a little bit weird in learning. And I'll tell you why in just a moment. But actually, you're going to find out why real quick. So what we have to pick to make this work for our sigma squared is an alpha term, which is a shape, and a beta term, which is what R will call a rate. The alpha term we can create using this nu sub 0. That's supposed to be a Greek character rather than a V, but to me they look pretty much the same. Script V. That nu sub 0 is supposed to represent your degrees of freedom total in your analysis, effectively, right? Or, sorry, degrees of freedom error in your analysis, effectively. So that okay. As a prior, we can go look at our data. We can look at how many parameters we have. We can go and sketch out what that should be. Oh yeah, that's my degrees of freedom. Then the next one, you could say, okay, for the rate, beta 0, the way we typically form it involves a value that we think the residual error variance should be. Oh yeah, why not? Why don't we just run the analysis another way? That's what I gotta say. Like, when have you ever gotten a regression problem and thought, I totally know the residual variance before running this. Because that's what a prior is. It's your belief, right? Anyone have that happen? Maybe in a textbook you've seen that happen? But let's be real, that doesn't happen. Right? But it does allow us to start thinking about what residual variance could be. So it helps us a little bit with more with how it would be for this. So let me ask you, as you're coming into Bayes, how do you feel? What should we choose for these priors? Does anyone have a belief that we should pick?
Something not harmful.
There we go. Yeah, do the least amount of harm, right? Hippocratic oath of Bayesians. The Bayesiocratic oath or something like that. So, I'm going to talk about, if you have no idea, you're right there with me. I have no idea either. So I started thinking of ways that we could do this. I think I came up with a way that might be okay. But let me just show you a little bit of what happens. I went back to our full model, right? I grabbed the degrees of freedom. I grabbed an estimate of our residual variance from our full model. And I plugged them in for priors. And I did that because I wanted to plot for you the prior distribution for sigma squared. All right, so here's sigma squared. The prior, when you plug in those values from our analysis that we did with the least squares, which again, if you're going to do that, why are you doing Bayes? But just go start somewhere. Here's what it said. The mode of that prior was about 58.33, and the MLE, the MLE, this is the part that came from the least squares analysis. Least squares and MLE are convergent for the result, was 63.19. Right, so it's a little bit lower. It's got a tail that goes in this direction. See how that works. Now, I think this is a pretty strong prior. And the reason why I think this is a strong prior is because if I'm already looking at my previous analysis, I'm sitting there thinking, that's a pretty high R squared, right? That's pretty informative that we pretty much signal from the data. Maybe it doesn't matter, I don't know. There is a complicating factor. So I'm going to change this in just a minute, but there's a complicating factor I want to cover when we start talking about how to implement this in JAGs. And that is, in JAGs, it doesn't just use sigma squared, right? It uses, for the normal distributions, it uses 1 over sigma squared, right? Which, just like in R, when the assignment character was the arrow back when I learned it, and I was like, forget that. When I learned this is how OpenBugs or the Bugs language did it, forget that. Who thinks in, if it's hard enough to think of a prior for sigma squared, it's even worse to think of a prior for 1 over sigma squared, right? What they call that parameter, 1 over sigma squared, is a precision parameter, right? So you can think of sigma squared as a measure of dispersion, like how wide a distribution might be. So its inverse is sort of the opposite of dispersion, and that's how precise your would be. It's sort of the dispersion. So precision, turns out the precision parameter follows a gamma distribution. Okay. How many of you are super fans of gamma? Oh yeah, I have gamma wallpaper at home. Right. Anybody have gamma pajamas, right? Nobody says that, right? It's just like, yeah, I love it. Like, no. Turns out the gamma, the parameters for gamma also have an alpha and a beta, 2 parameters. Also called a shape and a rate, although depending on which text you're reading about them, that rate one might be scale. And depending on what alpha and beta, depending on how the notation works, you may have to double check which is which. So what it happens to be is that once we pick our rate and shape from the inverse gamma on the scale that we're a little bit more familiar with, which is sigma squared, which is already hard enough, they are going to be the same for gamma too. Right? So that's one convenient part. Turns out when you do the precision parameter, there's just a few steps less you have to do calculation-wise to put this through in the algorithm. I think that's the motivation for it. I don't know 100% though. So this is what the gamma distribution looks like. You'll notice the range here. Also, this distribution goes from 0 up to positive infinity, but you'll see because we're 1 over sigma squared with it, it's like 1 over 65, right? Which is what that should be, right? And so when we looked at our previous analysis, it gave us a variance that was 63.55, I think. 1 over that is 0.02, and our prior mode is 0.01. And that's what it's saying. Questions, comments? Anyone hate this yet? Good. So, the part that was baffling me, though, was how do we make this a little bit how do we do least amount of harm? Because if you think about this, going back to sigma squared here, look at the range of where the mass of that distribution is. Right? It's basically saying there's like no chance you're going to find a residual variance that's less than like 25. Forget that, right? And likewise, there's not much chance you're going to find something bigger than 150. That seems arbitrarily enforced, doesn't it? Like if you were coming into this analysis and you're truly trying to be Bayes, why would you say your residual variance is between 150 and 150, literally 50 and 150? Not like, oh, that's just a sort of a relative term. That's literally the values it should be. That sounds weird, right? So what do we know about residual variance? This is where I was trying to think about this. I will tell you, this is my own writing. This is not, I didn't find this anywhere, so take that for what it's worth. But here's my intuition that I use for it. The residual variance itself, we can go and pick the maximum value of a residual variance happens when actually all the betas but the intercept equal to 0, right? What's the variance of y? Y's variance is going to be, has to be necessarily greater than or equal to the residual variance, right? So that's sort of that's a good anchor point for me at least. That doesn't mean we want our distribution to stop at y, because you think about if we think in the frequentist sense, what is the sampling distribution of the variance? Inverse gamma, right? It's a scaled chi-square. It's another way of, right? They usually talk about scaled chi-squares. I think there's an equivalence between inverse gamma and scaled chi-square if we constrain certain parameters. All right, so that sampling distribution of the variance is what I'm thinking. What if you repeated this over and over again and just looked at the variance of y, what type of range would you have? How many times do you calculate the standard error of your variance? Doesn't happen a lot unless you're in mixed models, right? But that's what we're working with here. So how do we figure that out? So what I went and did is I figured out the MLE of the variance.